Computer blurb. Okay. So, this happens a lot. This has happened over and over again in my life where I'm saying a concept that's founded in mathematical reasoning that most people aren't aware of. And because they're not aware of it, they dismiss it and claim that they know better. And then later, many, many years later, a physicist writes a book where they say part of what I'm saying. And they go on this whole junket of publicity. And then people say, oh, wow, how innovative, how insightful. And mathematicians got there first. This has been a long series of events that happens over and over again between physicists and mathematicians. It's kind of embarrassing. Um, when physicists were trying to take apart everything and look at each part separately, mathematicians had to explain to them that you're not going to be able to understand the totality of the system that way. That's called reductionism, is what you're doing. And the whole system, all the parts are going to interact in a way that wiggles toward a settling point, a point where all the forces are now stable, and that's called an equilibrium. And the only way you can find the equilibrium is through the system's dynamics, the incentives in game theoretic terms. And so mathematicians had to invent a word to tell physicists about this, and we invented the word holistic. Holistic thinking is what mathematicians do. And it's been 100 years now we're the ones talking about holistic thinking. And then I'll go talk to some festival kids who like to load in a van to go to Burning Man, and they'll be using reductionist thinking and saying the word holistic. And when I mention holistic thinking, they're dismissive because they don't understand the math. It's really funny. Um, so there's one of those concepts came up recently. A few months ago, I saw that there was a physicist who published a book saying part of what I've been telling people over and over again for a couple decades. And it's about information theory and the direction of time having this accumulation of entropy. What is entropy? If you ask the festival kid what entropy is, they're going to say it's chaos, disorder, dysfunction, things breaking down. If you ask a physicist what entropy is, they're going to say it's the cold, dark nothingness, stillness at the end of time, where there's no energy left to be used for any kind of useful work. They should learn mathematics. So let's look at the actual description of entropy, which was developed by mathematicians who invented statistical mechanics, which gave physicists thermodynamics. Over and over again, when a mathematician does physics, they finish the job. And, Hamilton and Maxwell, electromagnetism, no one's arguing about that. When Einstein came up with the idea for relativity, it was something Maxwell was already pretty close to. And Einstein had to go to Grossman to get the equations done. Usually when a physicist has trouble with something, they go to a mathematician and say, could you help me with this? And the mathematician says, oh yeah, let me grab that book off the shelf. We solved it a while ago. So here's one of those. In statistical mechanics, which gives you thermodynamics, which gives you entropy, the idea is that you have a box full of particles, and the particles all have velocities and momenta and positions, this high-dimensional space describing all of them. So you can place the moment of that box, the state of every particle, you can place that as a single point in a very high-dimensional space. You've got this many-dimensioned space, meaning many directions, and you're going to put a single point in that high-dimensional space where the coordinates in that space are encoding all the positions and momentums of all the particles in your box. That's called a state space. So you can look at the momentary state space of a box full of particles. And then another moment passes and the particles have moved. So they're now in new positions. Maybe some of them bounced against stuff and now they have different momenta. And so you move to a different point in the state space. And then a little bit more time goes by and you move to another point in the state space. And so you're flowing through the state space. And here's a couple concepts about state space. State space is limited. There's only so many positions and momenta vectors for particles. It's already a closed box. It doesn't grow or change. So we got that constraint. It is a confined space. It's really big, but it's still finite and static. And the other thing is that the flow of particles within your box, they're what's called a chaotic system, which doesn't mean it's random. That's not the same. Chaotic means if you start one way or you start a slightly different way, then over time you end up in very different places. So if all your positions and momenta are one way, that's one point in the state space. And if all your positions and momenta are just slightly different, just a slight rounding error, even just one particle in a slightly different position, that's a different place in the state space. And those two places in the state space, if you track them over time, they will evolve toward radically different outcomes. That split is chaos. So if you have a system where a small change in the beginning leads to a small change in the end, that's a linear system. But if a small change in the beginning leads to a constant growing change as you go further in time, that's a chaotic system. So the particles in this box are a chaotic system. And so two similar places must diverge. Okay, so if we're looking at the state space, two similar places, as time goes on, they split apart. But the state space is limited. It's finite, which requires that there were two states that were very far apart, which eventually come close together. Now, they're not exactly the same. They can't overlap. So even though they're very, very close together, they're going to diverge again. But it means that two past histories, which were radically different, produce a present moment, which is indistinguishable. You can't tell which past you came from. And that's true in every chaotic system. So let's get a little bit more concept here. The flow patterns in that state space. If you're mapping out every position of the state space and then see where the vector field pushes them as time moves on, where do they go? You're going to see flow, where a whole clump of them all flow in the same place, roughly. And you can see this on the grid of different two-arm pendulum positions. There's a divergence around the perimeter, and then there's islands of stability. And it's a fractal dimensioned space in that state space. So it's really cool stuff. But it means that if you have a cluster of possible present moments, you're not sure because your measurement device isn't accurate enough to tell which of these present moments you're in. Most of them are going to flow in the same direction for a while. Only some of them branch off. And then over time, more and more of them branch off. But some of them also re-merge. So if you track all the different potential moment now, the current moment possibilities for a hurricane, and then you run all those initial conditions through a weather model, you get what's called a spaghetti plot, where all these different hurricane paths happen, and many of them end up clustering. So even though you were uncertain about what's going to happen here, most of them end up merging back together in some attractor state later on. So you can have higher certainty about that future attractor state than you did about the past before it. So that's a concept from mathematics, is attractors or equilibria. That you're going to have a state in the state space that other states gravitate toward. And so we got that concept. Now we're going to talk about the statistical mechanics of what we mean by entropy. So entropy is the idea that if there is some macro feature that you're measuring, like the pressure on the walls of your box, which represents the atmospheric pressure of the gas inside the box, or the average velocity of the particles in the box, which is the temperature of the box. If you're averaging over the whole system, that's a macro state. And if you take the macro state values of every point in the state space, what you will find is that states which have an unusual macro state will tend over time to move into states that have a common macro state. That's basically the pigeonhole principle. You can look that up. So if there's a macro state for a particular state in the state space that's rare, and there's a different macro state in the state space that's very common, then as you evolve that system, as you move through the state space, you're going to go from the rare state macro measurement into the common macro measurement states most of the time. Most of the time, you will be occupying the state space in places that have this common macro feature, even though you started in a rare macro feature. And so what that looks like is if you had a box full of particles and they were all shoved to one corner, you got gas molecules all in one corner of the box. Well, as the state of the system evolves, those particles will tend to smear out and spread through the box. So most of the time, all the gas molecules will be spread out roughly equally. And you'll see roughly equal pressure on all the walls as every molecule strikes the walls. And you'll see a natural distribution of the velocities of the particles, and that'll be temperature. So most of the state space time, most of the time you're moving through state space, is in one of the common states. The macro state measurements are going to be normally the most common ones, even if you started in a rare macro state. That doesn't mean you stay there. You are moving through the state space ambivalent to what physicists measure the macro state to be. Regardless of what physicists measure the pressure or temperature to be, you are still moving on a strict path through the state space. And that means that even if you start out in a state that has a common normal macro measurement, you will eventually sometimes pass through states in the state space that have rare macro measurements. So even if you started out with gas molecules evenly spread out throughout the box, moving in all different directions at random, there will be times far in the future where all the gas molecules are in one corner again. Just like the DVD logo that bounces around your screen, eventually it clicks in the corner and bounces back. So it's not like you get to an entropic state and then stay there. You're actually moving through a state space that has rare macro states and common macro states. And because the common ones are so common, you spend more of your time there. That's all it is. You will eventually get back to rare macro states, and then you'll leave them again because you're going to keep moving through the state space. So entropy is not a final state. Entropy is just a statement about the average state of a system. If you just glance at it at any given moment, it's probably going to be in one of the most common macro states. That's all. It's not some directionality that's imposed and then you leave everything else behind. So now we can get into a little bit more about what entropy is doing. And this is what the physicist's recent book was alluding to. He's dipping his toe in this concept. But mathematicians, we've understood this for a while. So I'm going to go on what seems like a tangent, but it's a foundation. There was a guy named Frank Ramsey about a century ago, and he noticed that if you have enough stars in the sky and you allow just a certain amount of wiggle room in your measurements, you can have a big wiggle room. You get one number. The smaller your wiggle room, the more stars you need. But you can't ever get to zero wiggle room. That's impossible. You're always going to have measurement errors. So if you allow a certain amount of measurement error and you're looking at stars in the sky, there is a certain number of stars at which point you cannot avoid 3 in a row. 3 in a row is unavoidable if you have enough stars in the sky. Now, that doesn't mean all the stars are 3 in a row, but it means that ordered state of 3 stars in a row cannot be avoided. If you take one of those 3 stars and try and move them somewhere else, something else lines up. You can't avoid it. You filled out the combinatorial space. And he showed that in a more simplistic, understandable way in the idea of you have a party. You invite people over for a gathering. And there's 5 people who are showing up at your party. You got five people here. And each person has some kind of connection to every other person. All of them are connected in one way or the other. Excuse me. Either they already know each other or they're strangers. So we're going to represent that with a red line or a blue line. Every dot, every fingertip is connected to every other fingertip with a line, and we're going to have to color every single line either red or blue to represent whether they know each other or they don't. It's either or. So this is called the Ramsey coloring problem, or the party problem. And here's the quick question that Ramsey posed that has taken a very long time to answer. Can you invite people to a party so that there's no group of three who all know each other, and there's no group of three who are all strangers? Because if there's a group of three people who all know each other, they're all going to hang out together. And that's not, it kind of ruins the mood. They're in their own little cluster. It's not fun for everyone else. And if there's three people who don't know each other, then they're kind of awkward. It makes things uncomfortable. Okay, so we're going to make all the lines between all these 5 people, and we're going to have to color every single line either blue or red. And we want to color these lines blue or red in a way that no group of 3 is all red and no group of 3 is all blue. Can we do that? Yeah. Red around the outside, blue in a star in the middle. There you go. Wait, I didn't do that right. Yeah, well, anyway, you get it. Math. I'm trying to draw by looking at the screen. So that's the coloring for a graph of 5 nodes where you're avoiding subgroups of size 3. So it's G5, K3 in the Ramsey coloring problem. But what if you have 6 people at the party? Turns out you can check every single way you could color those lines. Every single coloring has at least 2 triangles that are all red or all blue. You have a triangle that's all red and a triangle that's all blue, or 2 blues or 2 reds, in every arrangement possible. Once you have 6 people at a party, you cannot avoid a group of 3 people who all know each other or a group of 3 people who are all strangers. You filled out the combinatorial space. There's no other options. Which means that once you get enough members in a group or enough objects in a system, there will be subsets of order that appear, and they cannot go away. There's no way you can mix it up to try and get rid of that order. The order is inherent to a system of that size. Whoa. And you might ask, well, what if you're trying to avoid groups of 4 of all the same color? Well, then the transition point is at 18. What if you're trying to avoid groups of 5? The answer is somewhere between 42 and 49. We haven't figured that out because there are too many options. We don't have a computer that big. we could try. Paul Erdős, E-R-D-O-S, he's grandfather of modern graph theory. He famously said that if aliens came to Earth and said that they would destroy us if we didn't find the Ramsey coloring of 5, then we could devote all the resources of humanity and all of our capabilities, and we could find out the Ramsey number of 5 and save ourselves. But if the aliens ask us to find the Ramsey number of 6, we should attack before they do. It's just too hard. So it's a very important concept, though, that once you have enough stuff in a system, you are guaranteed to always have a certain amount of order in that system. And the more stuff you get, the more order is going to happen naturally, intrinsically, more and more of the time, until it's 100% guaranteed. So you can look at the Ramsey colorings themselves, and you can see how much order usually happens in that state space. Remember I was talking about state spaces, all the gas molecules and that. And so now we got a macro state we can talk about which is the quantity of order. How many ordered subsystems are present in that state? In that state, in the state space, how much order do we see? Most of the state space is going to have a significant amount of order. And so as you're moving through the state space, you're going to see persistent order. So entropy is not order going away. It can't. Literally fills out the combinatorial space. You can't get rid of order, even when you go to maximum entropy. Ramsey says so, and he's a mathematician. We know better than physicists. And so now let's look at what I was saying about attractors in the state space. As you're moving through the state space, you're going to flow toward attractors. These are equilibria. It's like water rolling downhill. It settles at the lowest point. A ball at the top of a mountain is going to roll in one direction or another. You don't necessarily know which direction ahead of time, but you know it's going to end up at the bottom somewhere. There's going to be an equilibrium. So when you have a box full of gas molecules, the gas molecules are moving around on their trajectory, straight line trajectory, until they hit something. And then they bounce off like billiards. They're perfectly elastic collisions. Unless the box is kind of rubbery and it's absorbing some of that energy. So in that kind of system where you have perfectly elastic collisions, the most common macro state of the state space is for them to be all equally dispersed, roughly spread out evenly. And that's what we see with gases. If you put gas into a box, it spreads out evenly. That's how gas molecules work. That's the equilibrium of gas molecule dynamics. And so we solved that for statistical mechanics early on because it's not that hard. The equations simplify very easily. And I'm sorry, this is a long video. And then that gas molecule statistics was used to construct thermodynamics, mostly for the use in optimizing steam engines. And that became really useful, and so we kind of forgot about the other options for such a system. If you have a box with particles moving around in it, and the particles are sticky, they don't just bounce off of each other. If the particles have any amount of stickiness, then the equilibrium of that system, the natural attractor, is for them all to clump up. And that is an ordered structure. So whenever it's called anisotropy, whenever the forces are not equal in all directions, whenever you have an anisotropic system, the attractor is order. Order is the entropic state. What you expect at the end of time is an ordered structure. And we see that with gas molecules, not when they're in a little box. In a little box with just a few gas molecules, they just bounce around like billiards. But if you have like hundreds of trillions of gas molecules, they form a nebula because gravity only works in one direction. Gravity is not operating equally in both directions. So the unidirectional effect of gravity causes all those gas molecules to turn into a star, which is an ordered structure. The universe started out with evenly spread out gas, and then it turned into ordered structures. And that is what entropy looks like. Entropy creates order. Order is the natural consequence of entropy. Now people say, but I thought entropy was randomness and chaos. No. When you have a highly entropic state in the state space, then there is no difference that you can extract work from. Remember, it was people working on steam engines who were using thermodynamics. They wanted to extract work from the system. They wanted to get energy out of it. So once you're in a highly entropic state, there's no work that you can extract from it. You can't get energy out of it. But that's not the same as the system being random. Entropy is ordered. So let's look at some real-world examples where the forces are not billiard ball elastic conditions. when you got little hairs falling off and fuzz falling off and cat fur, and it's all being mixed around in your hallway, when those fibers hit each other, the natural flow of the system is just everything's bouncing around. That's the stable energy level of the system. So you don't get to claim that that's an insertion of work, because in a gas molecule system, you would have a continuous flow of particles because of the heat. You're not losing energy or gaining energy. So that we're going to do the equivalent, which is you got a bunch of fuzz in your carpet, and it gets kicked into the hallway where you got hardwood or tile. As that fuzz bounces around, every time it comes into contact, it tends to bind together. And so the natural entropic state of the fuzz in your hallway is a dust bunny, which is an ordered structure. And when you have those ordered structures, they have emergent properties. An emergent property is a property of the larger thing that wasn't written into the instructions of any of the small parts. You have the rules for each piece on a chessboard. None of those rules for each piece tell you how the chess game plays out. The way chess plays out, and the idea that like the center four squares are really important to control, those are emergent patterns observed at the macro level. So we have emergent dynamics of dust bunnies. And this is important. Dust bunnies want to grow bigger. As more fiber bumps into them, they tend to accrue more and more dust, and they get bigger. But at a certain point, the dust bunny's gotten so large, if it doubles in diameter, then it has 8 times as much fuzz, 8 times as much mass, but it only has 4 times the surface area holding it together. It's 2 times 2 for the surface area, but the mass is 2 times 2 times 2. So it got 8 times more massive, but only 4 times as much strength holding it together. So at a certain critical threshold, depending on how kinked up the fibers are, the dust bunny will naturally tear apart because it can't hold itself together anymore. And that's exactly the same kind of dynamic that we see in biology. Cells. Cells grow to a natural size until they subdivide. The reasoning behind why cells do it is because once they get so big, they only have 4 times the surface area, but 8 times the mass. And so their metabolism went up 8 times, but their ability to get rid of heat only went up 4 times. So they're overheating. They have to split to be able to exhaust heat. And that's why bacteria are smaller cells than mammal cells. We have bigger cells because we can support heat exhaust and nutrient exchange. The nutrient flow is also through your surface area, so that's the same physical geometric limit. Dust bunnies, it's a different kind of surface area. It's the surface area holding them together, but it's the same principle that their mass grew 8-fold, but their surface grew 4-fold, and so at a certain point they naturally subdivide. And it's not like they chose to do that. It's just this is physics operating under geometric constraints. So the dust bunnies split apart just like cells do. They behave like life. Unless there was some twist. If, like under the door, the dust bunny's under the door and it gets rolled by the door, one end of the dust bunny rolled more than the other end. This end traveled less distance. This end traveled more. So this end got rolled more than this end. They both rolled forward, but one of them was rolling forward more, which creates a twist. The twist binds the fibers together and makes it a stronger adhesion, which means this twisted dust bunny's tube can become stronger and grow larger. So it's like a dust snake or a dust eel. And those guys will get really big. You'll also notice that dust bunnies will tend to hide in corners because those are the places where they're least likely to get jostled. If they're moving around and getting jostled all the time, but they end up in a corner, there's not a lot that's going to pull them back out of the corner. So they end up accumulating in that corner. That's their attractor state, is to find a corner and hide there and just breed like bunnies. So these are emergent properties of statistical mechanics. These are the entropic equilibria of the systems, of the state space. And they behave like life. They behave exactly like life. And that's life.